right, for those people that take notes this way, this is 2.6a. This is 2.6a related rates. Two rates that are related. Josiah's going to read for us.
Suppose x and y are both differentiable functions of t.
Of what?
T.
Okay.
And are related by the equation y equals x squared plus 3. Find dy dt when x equals 1, given that the dx dt equals x.
All right, fantastic. So I need to find dy dt. I'm given x equals 1, and I'm given dx dt. So what am I taking a derivative with respect to? T. All right? Before we were all taking derivatives with respect to x. Now it's with respect to t. So I don't need you to write this notation, but I just want to show you that this is really what's happening. Oh dear. I am taking a derivative of that function with respect to t. I'm taking a derivative of that function with respect to t. Now, I normally don't write that step because then we just start getting going. All right? So, what's the derivative of y? Just 1, right? So it's 1, but the variables don't match up. So what do we get? dy dt is equal to, what's the derivative of x squared?
2x.
2x. But do my variables match up? No. So what implicitly pops out? Dx dt. Plus, what's the derivative of 3? 0. So that goes away. Now I just substitute in. Okay? So I need to find dy dt at x equals 1. So I just substitute everything in. So now I have 2 times, what's my x? 1. What's my dx dt? Tells me 2. All right, so I end up with 4. Now, what this is stating is that my x changes at a rate of 2. So x's go left and right, yes? So I'm moving to the right faster by 2 at whatever this x equals 1. And then this says dy dt at x equals 1. So what does y do? It moves which way? Up and down. So how fast is it moving? It is moving what? 4. And which way would that be going? It'd be going up 4. All right? So it'd be moving at a rate of 4 up and 2 to the right. That's what it's doing right there. All right? Pretty nifty?
Yes.
All right. So there's some guidelines that I'd like to read before we start reading how to read these kind of things. So Ansley and Becca are gonna tag team this one. Becca's number 1.
Identify all given quantities and quantities to be determined. Make a sketch and label the quantity.
All right. So on the given quantity, say something equals that. On the quantities to be determined, say I like to put like whatever it is equals question mark. All right. Number 2, Ansley.
Write an equation involving the variables whose rates of change either are given or are to be determined.
All right. So if it's an area equation, let's write the area equation and then go from there. Number 3.
Using the triangle, implicitly differentiate both sides of the equation with respect to time.
With respect to time. So are the variables going to match up very often?
No.
Like never. Okay. All right. Something will implicitly pop out. All right. And number 4.
After completing step 3, substitute into the resulting equation all known values for the variables and their rates of change. Then solve for the required rate of change.
All right. We're going to substitute things in once we know everything. Okay. Except for the one thing that we're solving for. All right. Here we go. So let's figure out how to read these statements. The velocity of a car after traveling for 1 hour is 50 miles per hour. Now, if I give you the distance is equal to x, my distance is x, and it tells me the velocity of the car traveling for 1 hour is 50 miles per hour. What is this 1 hour? That's our what? That's our time. So t equals 1 hour, right? T equals 1. But what is this velocity of the car? If I have distance, how do I get to velocity? I take a derivative. And the derivative of this x would be what? Let's see if we get this right. Dx dt, exactly. Because now it's with respect to time. All right, so my dx dt equals 50. That's what the velocity of the car is. See how that worked? All right, that's that reading thing that we're going to be working with right here. All right, the next one. Water is being pumped into a swimming pool at a rate of 10 cubic meters per hour. Well, if I have water in a swimming pool, what is that taking up? Volume. It's taking up volume. All right, so V is equal to volume. All right, V is equal to the volume of the water in my pool. But it's being pumped into a swimming pool at a rate. So how do I take a rate of volume? I take a derivative. So how do I take a derivative? dV dt. So dV dt is equal to what? 10. All right, it's equal to 10. Now, our units aren't they're not tested very often, but it is talking about the volume changing, so it is cubed. All right. If water were being pumped out of my pool, would it be 10 or negative 10? It'd be negative. Why would it be negative? Because it's taking away. My volume is becoming less. All right. If my volume is becoming more, dV dt is positive. If it's becoming less, dV dt would be what? Negative. All right. You see how that worked? All right. I'm not worried about the last one. Here we go. Who likes to throw things into a pond? I bet Miller does. Go for it.
A pebble is dropped into a calm pond, causing ripples in the form of concentric circles, as shown in figure 2.34. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4, at what rate is the total area A of the disturbed water changing?
All right. Fantastic. So, has anybody ever done this? Thrown something in water and seen these ripples come? All right. I never want you to think of them the same again. I want you to think calculus. I really do. I really do want you to think of the calculus happening. All right. It's beautiful. It's beautiful. All right. So let's read what's happening. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. So what did that just give me? The radius is changing at a rate of that. So what does that mean? Does that give me r equals 1? No. What does that give me? dr dt is equal to 1. All right? The rate of my radius is changing at 1. So that is a derivative. That is dr dt equals 1. All right, let's keep reading. When the radius is what? 4. So what does that say? R equals 4. Let's keep reading. At what rate is the what? Total area disturbed changing. So, what do I need to find? I need to find the rate at which the area is changing. So if it's a rate, it's kind of a derivative. And so what would I write there? dA dt. That's what I'm finding. I need to find dA dt. All right. So I need to find area changing at a rate. Yes? So what the heck is the area equation of a circle? Pi r squared. They will give you a lot of formulas on a related rate section. However, they will not give you that one. Okay, you got to know that one. All right. I know. How rude. Area is equal to pi r squared of a circle. Good. All right. We made it to 4th grade. All right. So now what am I doing with that? I'm taking a what? A derivative. So the derivative of A would be what? dA dt. Equals, this pi is that constant multiple. So what's the derivative of r squared? 2 pi r. But what pops out? A dr dt because my variables don't match. All right. So I'm taking it with respect to time. I'm taking a derivative with respect to time. So I need a dr dt popping out. Pretty nifty. All right. Now let's substitute in. So here we go. So I need dA dt at my radius equals 4. So now I have 2 pi. What's my radius? 4. How fast is my radius changing? What's my dr dt? 1. So I end up with 8 pi. Now, I want to talk about units real quick. This is, I don't usually talk about units, but I'm going to talk about it real quick. So on this one, my area is changing. So what would be my units? Feet, what? Squared per second. All right, it'd be feet squared per second. Did anybody notice anything? I want you to notice something. What's my area? Pi r squared, right? What's my derivative of that area circle? 2 pi r. What's that? Oh. So I'm going from 2d, and I take a derivative, I go to what? 1d. Oh, that's interesting. Keep moving. All right. Aaliyah, go for it.
Air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet.
All right, fantastic. So let's break this down again. Area is being pumped at a rate. Air is being pumped at a rate of that. So what does that mean? When we pump air into it, is that creating area?
Volume.
No, that's creating what? Volume. So my volume is changing at a rate of 4.5 cubic feet per minute. So how do I write that? That's dv dt is equal to, I'm going to call it 9/2 because I don't like the decimal. Okay. All right. And then let's keep reading. We're going to find the rate of change of the radius. Well, what does that ask for? What does that ask for? The rate of change of the radius. So what is being asked? dr dt. That's my question mark. That's what's being asked. And then, do they give me anything else? When the radius is 2 feet. So what does that give me? R is equal to 2. So that's the information that they give me. That's how I extracted what was said. You see how that works? All right. Now, it's being asked about a volume. I'm taking a dv dt eventually of a what? A spherical balloon. So it's a sphere. They will give you this one. But let's see if anybody remembers. What's the volume of a sphere? 4/3 pi r cubed. All right. So they will give you that on the AP exam or a test. But anyway, 4/3 pi r cubed. So what are we going to do with that? We're going to take a derivative. So dv dt, oh, sorry. What's the derivative of v? dv dt is equal to, this 4/3 pi is just a constant multiple, so I'm really taking a derivative of this r cubed. So what gets brought down? A 3. So now I end up with 4 pi r squared what? dr dt. All right. So now let's substitute in what we know. What is my dv dt? 9/2 equals 4 pi times, what's my r? 2. So now I have 2 squared dr dt. So let's do a little bit of math. 2 squared is 4. 4 times 4 is 16. So I got 16 pi over here. And what do I want to do with that 16 pi? Divide. So dr dt, when my radius is 2, is equal to 9 over what? 32 pi. And make sure pi stays in the denominator. All right? Now, why was this a positive 9/2? Why was my dv dt a positive 9/2? Because it's filling up. My volume is getting bigger. Does that make sense? If air was leaking out of a balloon, then it would be what? Negative. All right? I want you to notice something real quick, though. Volume is equal to 4/3 pi r cubed. If I take a derivative of that, I get this 4 pi r squared. Does anybody know the relationship? Does anybody know what 4 pi r squared represents? What? It's the surface area of a sphere. Exactly. So I'm three-dimensional. I take a derivative, and what am I now? Oh, that's a coincidence. No. All right, here we go. We're going to talk about an airplane. Hubin is going to read about an airplane.
An airplane is flying on a flight path that will take it directly over a radar tracking station, as shown in figure 2.36. S is decreasing at a rate of 400 miles per hour.
All right, stop. What was just read?
Decreasing.
So what was just said?
Rate is -100.
Okay, but what's the rate? There it is. ds dt is equal to -400. That's what was just said. All right. Keep going.
When S is equal to 10 miles.
So what was just said? S equals 10. All right.
What is the speed of the plane?
All right, so we need to find the speed of that plane. Well, if you look at my little picture here, it creates a what kind of triangle? A right triangle. So this is my y, that's my x, and this is my s. Now, personally, I don't use s very often. I usually use z there, but that's fine. So how do we find the speed of the plane? What would that represent? The change of what? You're there.
dx over dt.
Exactly. So the speed of the plane would be dx dt. All right, that's my horizontal, right? So x is representing there. The speed would be dx dt. All right. So that's what I'm doing. So I need to find dx dt. What kind of triangle does it represent again? A right triangle. Is there anything about a right triangle that we know? Oh, Pythag, that sounds good. So x squared plus y squared is equal to s squared. All right, I don't like the s, but we're going to use it here because that's what they give me. So what are we going to do with it?
Substitute.
I can't substitute in yet. I'm going to take a derivative. All right, so now I end up with, what's the derivative of x squared? 2x dx dt plus, what's the derivative of y squared? 2y dy dt is equal to 2s ds dt. Now, when I first started teaching calculus, I would make my students leave the 2's for some reason. However, guess what we can get rid of?
The 2's.
All the 2's. Get rid of all of them. All right. All right. Let's try to substitute stuff in. Well, do I know my x?
No.
Kind of, sort of, not really. But we could solve for it. If my y is 6 and my s is what? 10. My x would have to be what? It would be 8. It's a 3, 4, 5 triangle. All right. But if you had to use Pythag, you do 6 squared plus x squared is equal to 10 squared, right? So then you get x squared is equal to 64. X would be equal to 8. Negative 8. Negative 8 doesn't make sense because it's a distance. All right. So we get x is equal to 8. And then, do I know my dx dt? No, that's what I'm solving for. So it's dx dt. Is just not equals. Plus, what's my y? 6. What is my dy dt? They did give it to us. I'll see, Mr. Flick. What? No, that's my y. What is my dy dt? What does dy dt represent? The rate at which what? Y is changing. Is y changing here? No. So it's what? 0. The height of my airplane is always right at 6 miles because it said so. All right? Does that make sense? Mm-hmm. All right. So my dy dt is equal to 0. Is equal to, what's my s? 10. And then what's my ds dt? Negative 400. Why was it negative again? Because it's decreasing. All right. It's getting closer to my radar station. All right. All right. Let's do a little bit of math. 10 times negative 400 is? Negative 4,000. And then I'm going to divide that by 8. So dx dt is equal to negative 4,000 over 8, which can simplify to negative 500. However, negative 500 is not actually my answer because we didn't read too carefully. What was actually asked? The speed. What is speed? Absolute value of velocity. So I want to take the absolute value of dx dt, which would be what? 500. Pretty good? All right, fantastic. Why was it negative 500? I want to talk about it. Why was it negative 500? No, not necessarily left here.
It's getting closer to the destination.
It's making my x smaller. Okay? My x is getting smaller, so dx dt has to be negative. Does that make sense?
Mm-hmm.
If that thing were going away from the radar station, guess what it would be?
Positive.
It'd be positive, because now my x is getting what? Bigger. All right? See that makes sense? Okay. All right. Well, here we go. You're like, that was over hard. All right. I need another reader. Thanks, Gunner.
Suppose a liquid is to be cleared of sediment by pouring it through a cone-shaped filter. Assume that the height of the cone is 16 inches.
And the radius.
And the radius of the base of the cone is 40.
All right. Let's draw a picture. So draw a little picture of a cone. So the height of my cone is 16. And the radius of my cone is 4. Now, sometimes they try to trick you and give you a diameter. You want the radius. Okay? All right. Keep going.
If the liquid is flowing out of the cone at a rate of 2 inches cubed per minute.
All right. Let's stop there. What was just read? Liquid is flowing out of my cone at 2. What does that mean? What's negative? What's the rate? No. dV dt. A volume is changing. The liquid is a volume. So the volume is changing at 2. But what should it be? It should be what? Negative 2. Why is it negative again?
It's coming out.
It's coming out. All right. Keep reading.
When the level is 8 inches.
All right. Stop there. What does that mean? What does that give us?
The height is 8.
H is equal to 8. Good. All right. Keep going.
How fast is the depth of the liquid decreasing at that instant?
All right. What am I trying to find? dH dt. That's what I'm trying to find. All right. That's how we read that. Does that make sense? All right. Cool. Well, I need to eventually get to dV dt, and I got a cone. So I need the volume of a cone. Now, they will give this one to you. However, I want to see what we got. Does anybody remember volume of a cone? 1/3 pi r squared times your height. All right, we're almost there. Good. Now, what is being asked of this problem? What's being asked? By what? dH dt. How many variables do I have going on right now? I have 3. I got volume, I got radius, and I have height. All right? I only want to find dH dt. So I want to put everything in terms of height. So I want to get rid of my variable for radius. All right? So that's what we have to solve for. So this is where we create a proportion. So r over h would equal what? What is my radius? It tells me 4. What is my height? 16. So that could simplify to 1/4. So my r over h is equal to 1/4. You see how we did that? So what does r equal? All I do is multiply by h. So what does r equal? H over 4. So now I'm going to take this h over 4 and I'm going to substitute it in for r right there. See how we did that? All right. So now everything's going to be in terms of h. So now I'd end up with volume is equal to 1/3 pi. And then I'd have h over 4 squared h. Well, let's combine them now. H squared is what? H squared, right? So then h squared times h would be h cubed. So now I'd have h cubed over what? Not 4 anymore, but 4 squared, which is 16. And then I still have a pi, and I still have a 1/3 going right there. I would highly advise you not to try to combine the 3 and the 16. I would always keep this 1/3 out here. And here's why. When I take a derivative, this is going to be an h cubed or an r cubed every single time. So when you take a derivative, what happens? It goes away. All right? It goes down to the 1/3 and they go away. All right? It's roughly how that happens. All right? So I would highly advise you not to try to simplify all the way before you take a derivative. All right? Keep that 1/3 chilling and use them. So now let's take a derivative. What's the derivative of v? dv dt. And now I take a derivative of h cubed, so a 3 comes out front. So now I just have a pi. And then I'd have h squared over 16. And then what pops out? dh dt. All right, because I'm taking a derivative with respect to time, and I have h's. All right, now let's substitute in. What is my dv dt? -2 is equal to pi. And then what's my h? 8. So 8 squared is 64. 64 divided by 16 is 4. So now dh dt at when my height is equal to 8 is equal to -2 over 4 pi, which would be simplified to -1 over 2 pi if you wanted to. All right. Now, that's how fast my cone is dropping. When I have a height of 8, that's how fast whatever liquid it is dropping out. Okay? Now, I want to talk about this a little bit. We'll talk about it more later. Is it dropping as fast up at the top of the cone, or is it going faster? It's slower. What's it doing at the bottom? It's faster. All right? And we'll talk about that more as our time continues, but right now I just wanted to kind of briefly touch. All right? There you go. There you go. A lot of the difficulty is reading and understanding what you just read. All right?